We know that electromagnetic waves propagate in vacuum at the speed of light, and it does not require any medium to travel. Now let's see how electromagnetic waves can be predicted from Maxwell's equation. And how do electromagnetic waves propagate in a self-sustained manner? Let's say an electromagnetic wave is propagating in the x direction. Then if the electric field points in y direction, then magnetic field will point in z direction. Now let us consider a loop on the xy plane like this, and then apply Faraday's law for this loop. Let's say the coordinate of this point is x, then if this distance is delta x, then the coordinate of this point should be x plus delta x. And let's say the height of the loop is L. Now the Faraday's law tells us that the electromotive force induced in this loop is equal to minus the rate of change of magnetic flux through this loop. Now the induced electromotive force can be found out by this line integral. As the electric field here is acting in the y direction, the line integral here should be the height of this loop L times uy at this point x plus delta x minus height of the loop L times uy at this point x. So now let's find out the magnetic flux phi m through this loop. As the magnetic field is pointing in the z direction, the flux through this loop phi m should be equal to bz times the area of the loop, which is L times delta x. So let's put these values into the Faraday's law. From that we can see that the rate of change of y component of the electric field with x is minus the rate of change of bz with time. And taking proper limit, we can write this as the partial derivative of uy with respect to x. So let's mark it as equation number 1. Now let us consider a loop with height L and width delta x as before, but in the xz plane. And let's apply the modified Ampere's law for this loop. The modified Ampere's law tells us that the line integral of magnetic field around the loop is equal to mu naught times I of that loop plus mu naught times the displacement current. Now we can write this electric flux to be equal to area times the y component of electric field. And we can also set this term to be equal to 0 as there is no current in free space. The line integral around this loop for magnetic field can be written as the height of the loop L times bz at point x minus the height of the loop L times bz at point x plus delta x. Now putting these values into this equation, we see that minus the rate of change of bz with respect to x is equal to mu naught times epsilon naught times the rate of change of uy with respect to t. Now taking proper limit, we can write this thing to be a partial derivative of bz with respect to x. Let's say this is equation 2. Now if we take partial derivative of equation 1 with respect to x, we get this equation. And if we take partial derivative of equation 2 with time, we get this equation. And these two quantities are equal. So we can write these two quantities to be equal to, which leads us to this equation. This is the wave equation for the electric field. Now, from the wave equation, we know that this term can be compared to 1 by v squared. So, if we compare these two equations, we get the velocity of the electric field to be equal to square root of 1 by mu naught times epsilon naught. And as the electric field obeys the wave equation, the solution of this wave equation can be written as a function of x plus minus vt. Okay, so now here's a little exercise for you. By using equations 1 and 2, you have to show that the z component of the magnetic field too obeys the same equation. You can also verify that for this solution of the magnetic field, and also for a given wave whose magnetic field Bz is given by this equation, find out the value of omega over k. So we saw that electromagnetic waves can be predicted from Maxwell's equations. But how does this electromagnetic wave propagate in vacuum? Well, the changing electric field creates magnetic field, and the changing magnetic field creates electric field, which creates an electromagnetic wave that travels at the speed of light.